Welcome to Physics Review video number 2. This one is all about motion. And really, motion is all about observations. Mainly, we describe motion according to the position an object is with respect to the time that it's been moving. And we really wouldn't know about motion or really any change in this world without time. So time is going to be a big part of our study of motion, and this idea of rate of change of time and how position changes with time is going to be a really, really big idea. So this GIF on your screen has a cool image showing actually the position of the ball at different instances in time. So it creates this little trail. And when the trail shows the balls spaced out, that's when it's moving really fast. And when those little shadows of the ball are on top of each other, that's when it's moving slow. So before we get into distance and time, let's just think about kind of where we're going. We're going to start with linear motion, which is constant velocity or constant accelerating motion, and then we're going to think about projectile motion. So we'll start simple with our one dimension, our length dimension or our height dimension, and then we'll get complicated a little bit and merge those two dimensions and look at two-dimensional projectiles. No three dimensions, at least not for this course. So first, let's start with a little vocabulary. All motion can be described by an object's position in three dimensions: the length, or what we usually call the x dimension, the height, or what we usually call the y dimension, and then the width, which would be the z dimension. The distance that an object travels really is just how far it took to get there. So the colors are a little off on this, but for example, if I wanted to go home from BHS, I would go down Winton Road, and then I would go down Blossom Road, and we'd end up, in Burndom here, Burnland. And I could take, sometimes the traffic on Winton is really rough, so I'll go down Elmwood, and then I'll go up Clover, and then I'll cut up east, and then I'll go up Penfield Road. So I could take a variety of different paths to get from BHS to Burnland over here, and travel different distances. For example, if I drove 2 miles south and then 1 mile east, I went a total distance of 3 miles. However, there needs to be an absolute way to represent the difference in position between two places in space, and that is the displacement. So the displacement is a straight vector from start to finish. And on this diagram, we would draw it straight from Brighton High School all the way to Burnland. And I'm just going to make it really dark to show you that it's different from the distance. So the distance is always going to be greater or at least equal to the displacement. The displacement is this, as the crow flies, straight line from start to finish. So we would calculate this using our regular old Pythagorean theorem if we needed to. So a lot of the times I'm going to say d, and d can represent distance or displacement actually, depending on the situation. Most of the time, it's going to represent displacement. So describing motion comes in kind of two categories. We can describe motion as either constant velocity motion or constant accelerating motion. So a constant velocity motion means we're moving at the same pace. So the same displacement in equal time intervals, as is shown on this screen with yellow dots. So each of these yellow dots is 2 blocks apart. And this is called a dot diagram. This is one way of describing motion. Now, if it's accelerating, what's really happening is that the velocity of this object is changing with time. So this could be either the speed, it's actually speeding up, like is shown in these green dots here. So each second that passes, the displacement doubles actually, or the position that it was with respect to the previous position, a previous second ago, doubles. So we have this increasing at an increasing rate. The velocity can also change if the direction of the speed is changing. So for example, with the moon orbiting around the Earth or anything orbiting around the Earth, it is moving so quickly that it's kind of falling towards the Earth but missing it every time. And so the velocity changes each second because the direction changes each second. So these are two ways of describing motion. So if somebody asks you to describe motion, it's either constant velocity motion or constant acceleration motion. And this is an acceleration that's not zero. Now there are types of motion in this universe that are not constant acceleration motion, but we are going to focus on constant acceleration as this simple case for us to study in physics. Another way to look at these types of motion is through a graph of displacement versus time, velocity versus time, and acceleration versus time. And this got a little messed up apparently. So a constant velocity graph is a linear relationship. It moves the same displacement in the same period of time. A constant velocity graph would show a consistently the same velocity over time and zero acceleration. However, an accelerating graph would have this swoop, an increase at an increasing rate, so it goes farther each equal time interval. It would have a constantly increasing acceleration, so it would be linear in a velocity versus time graph, and it would have a constantly the same acceleration but non-zero acceleration. So this is the swoop, slant, oops, swoop, slant, flat physics salute. I forgot where my camera was. So we've got dot diagrams for representing motion, we've got graphs for representing motion, and then of course we have the equations that are in your reference tables. A equals delta v over t, which we actually saw back here. Vf equals vi plus at, d equals vit plus 1/2 at squared, and vf squared equals vi squared plus 2ad. You can use any of those formulas as long as you have 3 of the 4 things that are in them to solve for all sorts of fun stuff. Free fall is another type of special acceleration. So with free fall, our objects will increase with time. So they'll increase their speed with time, they'll increase their distance with time. I was just trying to find my pointer, and I drew a dot diagram over here of what a freely falling object on the surface of the Earth would look like over time. Now, some fun things about free fall. Free fall is a special type of acceleration that is only dependent on the gravitational attraction of the Earth and is ignoring air resistance and other things that really would probably affect the fall of, for example, in this GIF, an elephant and a bullet, it looks like. But both of them are going to feel the same acceleration, and so if they're both dropped from the same height, they will both hit the ground at the same time. Every object, regardless of mass, regardless of initial velocity, will fall with an acceleration of 9.81 meters per second squared down on the surface of the Earth. Now, down is going to become really important, and sometimes we'll call down negative, sometimes we'll call down positive, just like we saw in the previous video. Orientation and coordinate system is super important. So putting this together a little bit, we can think about projectiles. So we have our regular linear motion, which you can see here with the red. Now in the x direction here on the surface of the Earth, there's no force that's going to cause acceleration. So there's no acceleration. So we see equal spacing of the red dots here. However, we are on the surface of the Earth, so the y direction, this radially downward direction, is going to have an acceleration equal to negative 9.81 meters per second squared. So we see with the blue spacing, the dots increase their spacing with time. If we line up this regular linear constant velocity motion in the x direction with an accelerating freefall motion in the y direction and put them together, we get the path of a horizontal projectile. So it moves, the same distance each second in the x direction, but it moves a little farther each second in the y direction. And this is the classic parabolic path. So these projectiles will go some distance dx, typically also called the range. They'll fall some distance dy. So that's a horizontal projectile where all of the initial velocity is in the x direction. So if we have this generalized expression for the initial velocity in the x direction, it's vi cosine theta. For a horizontal projectile, theta is 0. So cosine of 0 is 1, and we get vix is just vi. There's another type of projectile called a vertical projectile, which is just your straight up and down, like spud game, throwing something in the air. So it starts off initially just after it leaves your hand with some initial velocity. It reaches a max height d max or dy max and then falls down. At that max height, Vf is 0. So Vf is 0 at d max y and at half of the total time in the air. So this symmetry is super useful because it also tells us that at the end of the flight, at the total time, Vfy equals Vi, negative Viy. So putting together this idea of just a linear motion or a horizontal projectile and a vertical projectile, we can also think about angled projectiles. This is your Angry Birds scenario where there's some angle theta that the projectile is being launched at. 0-degree case is your horizontal projectile case. 90-degree case, your vertical projectile case, the maximum time in the air. But this is that case kind of in between. And we did a lab studying the longest range and found that 45 degrees was that maximum range. So if you're going to set up a projectile problem and trying to solve something like that, you would make this XY chart. These things are always true. The acceleration in the x direction is always 0. The initial velocity in the x direction is always equal to Vi cos theta, and Vfx is always equal to Vix. If you need to solve for some things, however, time is probably really necessary. And it's really just gravity, the y motion, that dictates the time that an object is in the air on the surface of the Earth, because that's what actually stops it. That's what pulls it down. So you need to use the y side of this chart a lot more often. It's just a lot more useful because it allows us to solve for the time, and time is something that's really important in a lot of these. So we can fire our projectiles at different angles. We can fire our projectiles at different velocities. And if we fire them fast enough, they go into orbit. And that leads us into the next review. Hope you liked it. Have a great night.